Does anyone have any questions about at least this example so far? So basically 3 times an input is an example of a linear transformation from R1 to R1. It's not a terribly interesting example. It's an example that you're already pretty familiar with. Another interesting thing about this is what people generally call linear functions in things like algebra classes are not in general examples of linear transformations. The problem is like stuff that looks like mx plus b. The problem is the b. So this is just sort of a trick of the language. So it's as though when you're in algebra courses, you call things like y equal to 3x plus 7. You call y a linear function of x. It's okay to do that in that context. But the trick in the head is to realize that when you're dealing with linear transformations of vector spaces, that constant addition somehow disappears. It's a trick of the language, but what can you do? In the end, you're sort of stuck with how people call things, get some historical inertia about how things are named. So is this okay so far? I mean, it's just a simple example. The example that I really want to get to is not that one. It's just a special case of that example that I kind of want to get to.
Can I see the screen for a second?
The what?
Oh, just where you were writing for a second.
Yeah, so I went pretty far. So the function to check is just the output is 3 times the input. It turns out that that definition of a transformation is a linear transformation of that definition of a function is satisfying the 2 properties that we need for linear transformations to have. They're additive on inputs and they behave well with respect to scalar multiplication. If you think about this, the number 3 in front of the x, as it turns out, is not that important. Either you could have that number be anything you want, 7, -1, 0, these would all be examples of linear transformations. So just one example. So it's sort of the top end, it's the bottom end. When you're thinking about, what I really want to talk about is this business right here. A more concrete, at least in terms of the class, a more useful example comes from left multiplication of a matrix with a vector. So if A is an n by m matrix, A can be used to define a function from Rm to Rn by multiplying an element x on the left by A. And as it turns out, as the slide says, this scheme defines a linear transformation from Rm to Rn. Whenever something looks like how so, I guess I need to explain why I'm saying that. So I'd like to look at a particular example. Why does something like this work? Why is the statement that we just made reasonable? So just an example to kind of give it a little weight. Let's suppose that I don't necessarily want to be using square matrices all the time. I don't think that it hurts the example terribly to do that. So I'll give in to the temptation and just use a 3 by 3 matrix again. And the claim is that if x bar or x arrow, that vector x, is in R3, then if we define a function t, which takes as an input x bar, so sometimes with definitions you see like the extra pair of dots right there, so I'll go with that. It's sort of saying we're defining the function as being a multiplied by x bar. Is a linear transformation from R3 to R3. One thing I would point out here, it's easy to get confused on notation. Whenever I use that funny looking R, I'm always talking about the vector space. When I use the standard R, I'm usually talking about a row operation when you won't see a superscript. So why is something like this true? We'd like to sort of verify the 2 properties. So let's do that. So a couple things to remember. matrix multiplication distributes over sums of vectors. So those are just words, but you're about to see, I think, what that means in the concrete sense. If we wanted to check the first property, if we're thinking about linear transformations, if the vector v and the vector w are elements, are vectors, are in R3, then so I'm going to write down sort of a chain of equations. The way we've defined the function t of the vector v plus the vector w is equal to a times the sum of these two vectors by definition. Just in terms of symbols, I have to sort of say what I mean. Let v be v1, v2, v3. Just writing them down as a column. And let the vector w be w1, w2. These are just the numerical entries, just numbers. Yes, there's a question.
Excuse me, Professor, just why is the v vector and the w vector was defined as in a row instead of in a column?
Being a column rather than a row, I think you mean? Yes, they're vertical. Yes. Yeah. So it's typical when so this comes down to a choice of how you want to define linear transformations, as it turns out. So when you're talking about the language, when you're talking about the approach that's used in most linear algebra textbooks, including our own and most others you can find, you typically represent vectors as columns rather than rows because the multiplication of the matrix is occurring on the left. If you did it the other way, you would have to change everything. So basically rows, you want to get another column vector out of it, I guess I would say. So a 3x3 matrix times the 3x1 column winds up being a 3x1 column, which is what you want. If you define the vectors as row vectors, then you would have to your input would be on the left, and you'd have to rewrite the matrix A a little bit. Essentially, you would want you'd have a 1x3 row times the 3x3 matrix to get a 1x3 row. So in a case like this, it's a convention to do that, but it's a convention which basically we want in order to you have to make some decisions about how you wind up doing things, I guess is the way to say it. I mean, I don't know if that answers the question. There's no deep theoretical reason why that is or why we're doing that right now. It's mainly a convention so that the input and the output are vectors. So when you multiply on the right a 3x3 matrix by a 3x1 column will generate a 3x1 column. So the inputs and the outputs are both vectors in the language that we're using. Does that make sense?
Oh yeah, just the thing that I want to express is that the reason why I question this is that I think the rows, the column come from the equation of a plane or a vector, right?
Yeah, I mean
they are right in column instead of in row.
You could view it that way as well. I mean, that's the point of view that we would have taken earlier.
Okay, sure. I will stick with the convention, I guess.
Yeah. So when we're at this point, if you have v being this and w being this, then v plus w, you just add up things entry-wise, and you get v1 plus w1, v2 plus w2, v3 plus w3. So the transformation on v plus w, the way that we've defined it, is a times, so I need more room, is a times v plus w, but in in more filling in a bit more detail, what does that look like? You have a matrix A times V plus W. You're multiplying on the left. V and W were vectors. We go back to the first statement, matrix multiplication distributes over sums of vectors. And so that's what we're sort of saying here. And so we distribute the A. And by definition, that's the same as the sum of the two transformations. And so that particular property isn't that surprising, and it follows from something that we kind of want to be true about the matrix multiplication. And for the other property, we let K be a scalar, be a number. T of KV, so as usual, V is a vector, is equal to what? Well, we can check. I think in this case, it's sort of productive to have sort of a formulation for V. K times V. So I need to remember what A is right here, but K times V is just K times each of the entries. So that's KV1, KV2, KV3. So let me go up here to remember the matrix. 1, 2, 1, 0, 1, negative 1. And I guess the last row is 5, 1, 2. If you think about matrix multiplication for a moment, several ways of sort of decomposing that. What I'm going to wind up doing is formulating the multiplication in terms of the weights. So I'll view the product as a linear combination of weight times column. It's just easier, requires a bit less computation to do it that way. If you think about the right-hand side of that equation for a minute, you notice that each of these particular vectors has a scalar k. It's reasonable to think that you can pull out that k, that the k distributes. In fact, it does. And you wind up with this right here. If you think that's right. So we wind up with k times this linear combination of column vectors from A. So it's negative 1 right there, I guess. Yes. And so if you recognize that linear combination, you realize that that's really the same as A times V. So I've sort of omitted a step there, but that's what it is. And so this particular point, I think, winds up being important, that if you have a matrix, then that matrix defines a linear transformation by multiplying vectors on the left by the matrix. If you think about things by analogy, that's really not so different than multiplying an input x by a number on the left. You're multiplying by a matrix rather than a number, but sometimes you can think about numbers being like a 1-by-1 matrix. So does this make sense so far?
Sorry, can I see the image again?
Which part?
Just the last part you were writing.
That right there?
Yeah.
Yeah, so I guess the only point here is that A times the scaled vector V winds up looking like this because of the matrix multiplication. You can factor out the K, as it turns out. And if you do that, when you pull out the K, what you're left with is K times this linear combination of vectors right here. But that linear combination of vectors is recognizable as just A times V. And so that's kind of where we're at. So that verifies, in a sense, the second property. So T of K times V is basically the product of these matrices. We verified that's the same. I guess I should write one more thing down. That's the same as K times T of V. So, we verified that you can pull out the constant. So again, linear transformations, turns out, are the type of function from vector space to vector space that preserve the essential properties of the vector space. So when we talk about abstract vector space, we'll talk about this in more detail. But again, these two properties, that they're additive, that a linear transformation applied to a sum is the sum of linear transformations, that a linear transformation applied to a constant times a vector is that same constant multiplied by a linear transformation applied to the vector. Those are the two key properties that linear transformations have. And in this case, it turns out, what we're thinking about here, it turns out that any matrix A is going to define a linear transformation from a vector space to another vector space by left multiplication. So A times a vector where A is on the left, that's a linear transformation. So, what does it mean that it's true? One thing that I would point out here, that third point, is if you identify matrix multiplication as being associated to some kind of function, you can very quickly show that matrix multiplication is associated. And the reason for this is that what you're going to wind up realizing is that matrix multiplication is in some way associated with the composition of functions, which is associated. Maybe I'll have that be an exercise at some later point in time, but that's probably the proper way of viewing what we're talking about with associativity of matrix multiplication. What final set of comments? We've noted that every matrix can be used to define a linear transformation via left multiplication, but the question might be the other way around. Does every linear transformation define a matrix? So if you start with a linear transformation, is there a way somehow to associate a matrix to that linear transformation? So in a moment, we'll see that the answer to that is yes, but you have to make some choices to be able to do it. It's important when you're thinking about how we're sort of doing the association to identify what those choices are, and then think a little bit about what would happen if you made a different set of choices. So, what I would say is that, sort of the takeaway from that set of slides, the takeaway from this verification, I think is the first sentence right here. Every matrix via left multiplication can be used to define a linear transformation of functions. Again, it's a type of function from a vector space to a vector space. It's natural to wonder whether or not you can go the other way. So if you start with a linear transformation and you come up with a matrix which represents it, that's kind of what the goal of the next slide is supposed to be. So does that make sense as an idea?
So essentially, every matrix can be defined as a linear transformation, but saying like the inverse of that is not always true.
It will be true, actually, but it's a complicated story. So when you start with the matrix, the set of slides is, as you say, essentially saying that if you have a matrix, then you have a linear transformation. If you define that linear transformation via left multiplication by that matrix. So there's no ambiguity about that. There's no choices to be made. There's nothing to be done there. You just have to verify that left multiplication acts in the way that you expect it to for a couple of key properties. This is just a question of sort of working through the details and realizing, I guess for the first property that matrix multiplication is associated. When you're talking about the other way, you're on the right track. The question is, if you have a linear transformation, is the converse true? If you have a linear transformation, can you define a matrix coming from it that represents it somehow? And the answer is yes, in a sense, but the matrix that you will define depends on choices that you make about the vector space, if that makes sense. If you make a different set of choices, you might represent that same linear transformation with a different matrix. So the difficulty is there's an ambiguity about how that linear transformation is to be represented. And so basically you have to think a little bit about the choices that you're making in terms, like when you go through a process and try to develop a matrix which represents a transformation, you have to sit and think about what choices you're making in order to do that. If you can identify what those choices are, then maybe it's possible to say some things about how the different choices you make are related. How they're related, we're going to wind up talking about, but I don't think we're probably going to talk about that until probably about week 5 or 6 of the course. But be aware that that idea is there. Does that make sense?
Yeah, thank you.
Yeah. So any other questions about the idea, what we're trying to achieve with this? So the next set of slides I'll go through, what I would say is that there are a couple of places that I'll probably need to provide some input. You have to be patient with the next set of slides because there's kind of a lot of detail. So let me bring them up. And they're technical. So let me show you what I mean. They're technical, so I'll probably only deal with the 3x3 case for the sake of simplicity, but you can imagine how that might extend to the n by n case. So we pick up here where we left off. So we've already associated a certain linear transformation to a matrix. So if you're thinking about things in symbols, in some weird abstract sense, we can take a matrix and associate to it a certain linear transformation. With the last bullet point, we're going to try to go the other way. There's a question about it. So if we start with linear transformation, start with a function, can we associate to that linear transformation a certain matrix? And so as we do this, the thing that I hope you remember is how matrix multiplication is defined. It turns out that matrix multiplication is completely essential when you're trying to figure out how you associate the matrix. So I'd like to start by trying to explain how indeed we would associate the matrix at all. And I would like to point out the particular choice that has to be made in order to carry out the association. So, we'll start by thinking about just a linear transformation T, which takes vectors X from R3 to R3. So again, just the column formulation. So when thinking about R3, you might notice that any vector V can be written as a linear combination of these vectors. So this is usually a point where I have to stop because we've not really talked very much about linear combinations. So we talked about linear combinations in the context of, we did a problem yesterday involving linear combinations of matrices. So what I mean by that is if you have those 3 vectors, then if you have any vector, it's possible to write down a weighted sum of the vectors that are in that braced list, so that the vector that you're talking about is equal to that weighted linear combination. So I feel like I have to actually do that. I feel like I have to actually show this. So this is sometimes called the standard ordered basis. This is the basis that people are usually thinking about when they're thinking about R3. 1, 0, 0 represents the x-axis. That's the way most people want to think about it. 0, 1, 0, usually people think about that as representing the y-axis. 0, 0, 1, people think about that as representing the z-axis. And so anything on the x-axis can be written as a multiple of 1, 0, 0. Anything along the y-axis can be written as a multiple of 0, 0, and so on. So, why is this true? How would you come up with a linear combination? So let's just see it. Let V be a vector in R3, so I'll write it this way. Now, remember that V1, V sub 1, V sub 2, and V sub 3 are just numbers. Then V1, V2, V3, the vector V, is equal to V1 times 1, 0, 0, plus V2, 0, 1, 0, plus V3, 0, 0, 1. So there's your linear combination, right? Now it turns out that this linear combination is unique. If you're dealing with when you're dealing with that set of vectors, The set of vectors that are in the braces in that slide, this is sort of a minimal set of vectors. This is an example of a basis for R3. So for example, if you actually had numbers, if you have the vector 3, 7, -5, what we're saying is that's the same as 3 times that vector plus 7 times that vector plus -5 times that vector, just an example. So, we're able to somehow take a vector in R3 and decompose it into this thing that we're calling a basis. We're going to have a lot more to say about vector space basis next week, but for now, just think about it as a minimal set of direction or a maximal set of directions for the vector space R3. You can't really remove any of the directions without losing some information about R3. You lose a direction, and so any vector contained within R3 can somehow be written as a combination of vectors. You can decompose a vector into a weighted combination of these various basis vectors. That's sort of the way to think about it. So, back to the slide, there's a lot we might say. Sure, I go back to where I want to go. Oops, too far. Okay. So again, sometimes this set of vectors is referred to as the standard ordered basis for R3. We haven't really defined the term yet. We verified that the vector V can be written at least as a linear combination. Uniqueness, I'm not gonna bother with right now. So what does this mean? The linear transformation T takes vectors in R3 to vectors TV in R3, right? It's a function. The input is a vector in R3. You're writing the output just formally as T of V. The second point, the elements in the range of T are going to be defined by how T treats the elements of the standard basis. So I mean by that something specific. What that statement means is that in order to know T of V for any vector V, all you need to know is what T does to 1, 0, 0, what T does to 0, 1, 0, and what T does to 0, 0, 1. And the reason is this. If V is, so I'll substitute, so if V is any vector in R3, say, we represent V with a column that looks something like this, then T of V, the vector V, is the same as T of V1, 1, 0, 0, plus V2, 0, 1, 0, plus V3, 0, 0, 1. Since T is a linear transformation, you can take what's inside T, you can take the input, and T sort of splits everything up. So remember that the linear transformation of the sum of vectors is the sum of the linear transformation evaluated on the vectors. Also, you can pull out scalars like the ones that you're seeing here, the V1, the V2, and the V3. So since T is a linear transformation, T of V is equal to V1, T of 1, 0, 0, plus V2, T of 0, 1, 0, plus V3, T of 0, 0, 1. So basically, once you know how t evaluates on the basis, once you know how t evaluates on the basis, you know how t evaluates on any vector. That's one of the virtues of having a basis. So do people have questions about this so far? Remember, in order to convince yourself of this, just realize that all you have to think about is like, well, look, in R3, I can write any v as a combination, as a weighted combination of my vectors that are in that collection of vectors that we're discussing. Since t is a linear transformation, you can kind of split the sum. And what's revealed by this calculation is that all you really need to know if you want to know the output, if you want to know what t of v actually is, all you really have to know is what t is on the individual basis vectors. If you know that, then you know the output. So that's sort of the reasoning. If you have questions about the reasoning so far. Now, there's one thing that people should point out. People might notice, about what we're trying to do. Is this the only basis for R3? So it seems like a reasonable one. I mean, it's a basis that most people would choose for R3, if they were left to their own devices. And the reason is that, the vectors that you're talking about here that are in this collection of basis vectors are at right angles to each other. They're also of unit length. It seems pretty reasonable to write any vector as a combination of these vectors simply because it's really easy to do. But it's not the only basis for R3, but the calculation we're about to do depends very much on this choice. And so when you're talking about associating a linear transformation to a matrix, it turns out that the choice of basis very much depends on how that matrix looks. So the linear transformation doesn't change, but the matrix might. It depends on your choice. So, when we make this particular choice, I don't want to sort of get into making too many choices right now, just making this one. I just want any association, just to kind of give an idea about how this stuff works. Any association will do. So the statement, the linear transformation takes vectors to TV. The elements in the range of T are defined by how T treats the elements, how it evaluates. So because of what we're writing down, I'm just going to make the decision to call T of 1, 0, 0. I'll call it the vector ABC. T of 0, 1, 0. I'll call that the vector DEF. T of 0, 0, 1. I'll call that the vector GHI. These are just choices. Call them what you want. There's a reason to sort of change the names later, as we'll see, but I need to call them something. And so basically what these equations all represent is these are giving outputs for T evaluated on the individual basis elements. So, where does this actually get you? Well, like before, I think I should sort of change the notations. Give that, like if V is equal to that linear combination, then T of V is this. So we kind of already know that if V can be written in this way, and because T is a linear transformation, it's possible to pull V apart under T. So if we happen to know what T on the individual basis vectors looks like, then we can say something about what the output looks like. But we have already decided what at least in an abstract sense, we've decided what T evaluated on the basis vectors actually looks like. We've given these vectors names. So T of 1, 0, 0, we're calling that the column vector ABC. T of 0, 1, 0, we're calling that the column vector DEF. T of 0, 0, 1, we're calling that the column vector GHI. So this is what T of V actually is. It's a linear combination of the values that T takes on when you plug in the basis vectors. So, if you stare at that for a minute, you'll realize that what you're looking at is, you realize that what you're looking at on the right-hand side, this piece right here, you realize that what you're looking at is in reality that right there. Why is that? remember. So you have A, B, C, D, E, F, G, H, I. If I multiply this matrix on the left by the vector K1, K2, K3, matrix multiplication, the way that we've defined it, is equal to K, ABC, plus K2, DEF, plus K3, GHI. So these two things are the same. So, if you go back up to where we were at, the idea behind matrix multiplication basically comes from formulas like this. So the goal in some sense is to define multiplication in such a way. I mean, you might think about the goal of the definition, why you would be prompted to define matrix multiplication in the way that we're talking about. You might think about the goal of it as basically being to try to represent linear transformations as matrix multiplication. So it gives you the definition. So if you know, or if you choose a basis, if you know what T is on B, if you define matrix multiplication in the way that we did yesterday, then it is possible to represent a linear transformation by left multiplication of the matrix. Is this okay so far? It's chosen, the way that we're multiplying is chosen in such a way so as to do this, like you were trying to do this, if that makes sense. Is this okay so far? So that's the goal. That's why it looks the way it does. So it's about 9:50. I can talk a little bit more about the slides, or we can move on. I feel like I need to move through some other stuff quickly. I don't want to spend as much time. I would encourage you, so I'll talk about this for the next 10 minutes, then we'll move on, maybe in the next 5 or 8 minutes, and then we'll move on. I think that the slides, if you're interested in this sort of thing, are important to read, to think about a little bit. On the other hand, they're pretty technical, they're pretty hard to read because you've got to keep track of a lot of things. So you probably want to give yourself some time to do it. The sort of material that we're talking about won't really appear on the web work today, but I feel like people at least need some motivation to explain why matrix multiplication looks the way it does. And in a sense, the answer is this. If matrix multiplication is defined the way that we have it, then there's a correspondence between linear transformations and matrices. So that's the goal. If you define it in some other way, it's not going to be true. So does anyone have any questions they'd like to ask? Any concerns so far?
I have a question. Sorry, I try to kind of make a whole sense of what we just went through each time, just so I can have a better understanding. So essentially, from that last component, we're just describing how vectors can be what's it called, written in I don't know what kind of matrix notation, with IJK, and that can also have a transfer, you can have a transformation with that vector and it still be the same format.
Yeah, I mean, I think what you might want to, I think I understand, but I think what you might want to say is that if you have a linear transformation is this abstract function, right? You don't know much about it. It's just some function. It turns out that it turns out to be possible to take a linear transformation and associate to it a matrix, which does the same thing as the transformation when you multiply on the left by the matrix. So it's just that's all we're trying to describe how that might be done. And so the way that it's done is that if you choose a what I want to call a basis for, in this example, R3, then the action of the linear transformation on the basis dictates what the columns of the representing matrix look like. So, back to Yeah. So what we're going to say is that this guy right here is the matrix which represents T with the choice of basis that we're making. So all that you're really seeing is just a description of how you move from a linear transformation to a matrix. When you take that matrix and you use that matrix in such a way so that you're multiplying vectors on the left by that matrix, the effect is the same as plugging in the vector into the linear transformation. The reason why you might be prompted to do this is because matrices and matrix multiplication is pretty easy computationally.
Are these like kind of notions to understand
Yeah.
rather than in actual practice, like rather than what if we have like a problem for instance, like that we would have to like be able to be able to like indicate, be able to tell why a linear transformation can be associated with the matrix.
Yeah, so I guess what I would say is at this point in the class, I think they're just ideas to understand. I'm hoping to give evidence that a linear transformation is associated with some matrix. And the reason why this association is possible is because we're thinking about matrix multiplication in a certain way. It will become practice later. It will turn out that, and it will become practice when we start thinking about the choice of basis. There are particular examples that I would want to talk about later in the course where you're choosing a certain basis and the representing matrix has certain qualities. That choice of vectors, that choice of basis vectors winds up being important. Right now, there's nothing I can really ask about this in terms of problem. I guess I could give you a formula for a linear transformation and ask you to represent it as a matrix of some kind. And in a way, what you're seeing in the notes is kind of giving you it's kind of giving you a recipe for doing that. But it's, right now, probably I would think more about these things as being, it's kind of being ideas. So maybe we'll do one example, maybe toward the end. But is this okay? I mean, that's kind of what I have in mind. If that answers the question.
Yeah, thank you.
So let's, I can continue or I can pause for a minute. I did want to talk a little bit more about matrix multiplication, but maybe it's worthwhile, maybe sort of hammering down the detail here about the relationship between linear transformations and matrices. So let's just look at R3 again. Suppose we've got a transformation, and I'll use the notation from R3 to R3, the domain and maybe the range space. So this is a linear transformation. And I'll give you a formula for it. Maybe T of a vector V. Maybe that's just V1 plus. So if it goes from R3 to R3, I need, I need to have some, so let me do it this way. Maybe I'll make it easy. I'll make it easy on myself. Let's go from R3 to R1, where T of the vector just collapses everything down to the first component. Maybe the vector V is V1, V2, V3. So if we're looking for, a matrix which represents T. If we're looking for something like that, if T goes from R3 to R1, what dimensions would we need if we want a matrix A, which does the same thing as T? So basically, we would want A times B should be a number, should be in R1, and it takes a vector as an input. So how many rows should A have? How many columns should it have? So A should be a 1×3 matrix. It's kind of an odd looking matrix. It's a row matrix, a row vector. How do you actually find that matrix? Choose the basis. 1, 0, 0, 0, 1, 0, 0, 0, 1. What does T do to each of these things? T of 1, 0, 0, it's just 1. T of 0, 1, 0, because you're projecting onto the first factor, is just 0. T of 0, 0, 1, again, because you're just projecting onto the first factor, is also 0. And so using the sort of recipe that we have, what we're thinking about in the representing matrix, the 1×3 matrix, you have a vector here, that goes here. It's sort of an odd looking vector, it's just a single number. You have a 0 vector right here, put that right here. You have 0 right here. And so that's A. And so you can check, if you take A, and if you were to multiply it by any vector in R3, you take row by column in this case, and you can do it lots of ways, but if you take just row by column, you have 1 times V1 and 0 times the other 2. So you get V1. So all this is really saying is that, again, the recipe is choose a basis. Look at what happens when T acts on that basis. The vectors that T generates as outputs on the basis are the columns of the representing matrix. And so when you write down the representing matrix, you can always check that the representing matrix does the same job as T's. That's all we just did. It's just a very funny looking representing matrix, mainly because the image space is R1. It's a 1×3 matrix. So again, the discussion that I'm trying to entertain here is like, why does matrix multiplication work the way that it does? The answer that I think that I would like to convince you of is that it works this way because we want to define it in such a way so that there is a correspondence between matrices of certain dimensions and linear transformations of vector spaces that we can move between one and the other. So that's kind of the point of the discussion. I'll move on. I think I'm going to move on pretty quickly. It's about 10. I'd like to discuss one more thing today before we're done. I don't want to get too bogged down. Depending on how you view this sort of thing, the next sort of slides might be difficult to follow, but I'll go over them anyway. Let's see. Right. So, when we're thinking about linear transformations and matrix multiplication, you're usually thinking about the product of matrices. So, if you have T1 and T2, maybe they're both linear transformations. Again, we're restricting to the case. We're just thinking about R3. We can look at the composition of functions. If you remember how composition works, when we compose T1 with T2, we take first T2 followed by T1, starting at R3. So T2 takes this vector space, this R3 into R3. T1 follows it by going from R3 to R3 again. And so the domain of the composition is R3 and its range is also R3. So, first of all, is the composition even a linear transformation? It turns out that it is. I don't really want to delay too much and check these properties right now. Maybe that's for a later assignment. I would like to sort of move through this set of slides pretty quickly. So the next point, we'll write down the matrices which represent two linear transformations. We don't really need to go through the process in detail again because we've already done it. T1 and T2 both have 3 by 3 matrix representations. So how do they look? You know, we can. I'll give you a formula for them a bit later. It's right. Maybe it's right here somewhere. Yeah, it's right here. So basically, T1 is represented, let's say, by this matrix right here. T2 is maybe represented by this matrix B right here. I'd like to think a little bit about the matrix which represents the composition. And again, if you're dealing with a linear transformation, which the composition actually is, all you have to worry about is how that composition acts on the basis vectors. I'll choose the same basis. You're still talking about 1, 0, 0, 0, 1, 0, and 0, 0, 1. First, you note that any vector v can be decomposed in this way. And so when the composition of functions acts on the vector, if it is a linear transformation, then it's possible to pull out scalars, so you wind up with this decomposition. So what you should be seeing here is something which looks very much like what we've done so far. The only thing that's really changed is the name of the linear transformation. So in order to understand how the composition acts on that vector, what this equation is saying is all I really need to know is how the composition works on the basis vectors I'm dealing with, the basis vectors I chose. We'll proceed sum n by sum n. I think I only did one example of this. How does T1 of T2 of 1, 0, 0 work? We've decided that the representing matrix for T2 looks like this set of B's, and the representing matrix for T1 looks like this set of A's. So T2 of 1, 0, 0 is just left multiplication by this matrix. You can use the definition of matrix multiplication to eventually convince yourself that this implies this, but again, don't want to delay too much. Some of these calculations probably worthwhile to sort of mess around a bit on your own with. So that's T1. Similarly, there's not a lot of difference in the approach, which is why I only did this one time. T1 of T2 of the second basis vector looks like this. T1 of T2 of the third basis vector looks a bit like this. And so basically what you're getting are the columns of the representing matrix. I mean, again, the 3 equations look complicated, but you can check that they basically come from this, where matrix multiplication is defined in the way that we're trying to describe. So what I'm saying, I guess, here is that the representing matrix for T1 of T2 is just the product of the matrices which represent T1 with the matrix which represents T2 in order. So when you think of things this way, again, the idea behind matrix multiplication is that it has to be defined in such a way so as to achieve this correspondence. If you compose linear transformations, what's the representing matrix? The representing matrix is the product of the individual representing matrices under matrix multiplication. So again, that's the takeaway from the slides. The main thing to worry about going forward is that the representing matrices, they depend on a choice of particular basis. If one makes a different choice, you get a different set of representing matrices, though the basic thread, the basic thread of the argument works the same way. So again, what I'd like to say about this, that's the takeaway, I think, from the slides. We're going to wind up talking a little bit more about the effect of changing the basis on these representing matrices a bit later when we have a bit more time. So I guess, are there any questions about this so far? You're not really going to do any problems with this right now, so don't be too worried about that. It's probably worthwhile, if you're interested in this kind of thing, to go back to look at the slides to explore some of the detail. A lot of the stuff that we're going to wind up doing, of a more conceptual, more theoretical nature, will involve a lot of matrices and symbolism that kind of looks like what you see on these slides. So it's important to be comfortable at least with how to interpret the symbol, to kind of get practice with it, to think about it a bit. So I think I'll probably leave this set of slides now, unless people have additional questions. So go back and read them, think about it a bit. The next set of slides has to do with, maybe something that's a bit more tangible. So we're going to be going back into a world where we actually have some fairly concrete matrices to multiply and to think about. So when I write down ERO, I mean elementary row operations, and I want to describe here what I'm calling the matrix form of these elementary row operations. So again, remember from an earlier lecture, when row reducing a matrix, there are three reasonable elementary row operations which are used either in, mostly if you're doing Gauss-Jordan elimination. When you use this notation, the first one that means swapping rows. The second one means multiplying row by non-zero constants. And the last one means replacing a row, with a certain linear combination of rows. And so you played around with that, I think, on the homework. We discussed it a little bit in class, did some things with it. So we kind of know what the symbolism means. The row operations that you're talking about here gradually transform matrix A into a matrix which is row reduced. If you use all three, you're generally out to discuss the reduced row echelon form of the matrix. If you're talking about Gauss-Jordan elimination. As it turns out, each of these elementary row operations corresponds to left multiplication of A by something called an elementary matrix, which I presently will define. So let's just start with the matrix A. This particular matrix, you'll notice, is it's coming from some system of equations, probably. Maybe it's an augmented matrix. If you look at this particular matrix, if you're thinking about how to row reduce it, if you want to use Gauss-Jordan elimination, you would generally start at the first pivot. But the problem with this particular matrix is that the first pivot is 0. So you can't really use that first pivot to do much of anything at all. So what most people are going to do when they're confronted with a particular matrix like this is that they're going to swap row 2 and row 1, or maybe more symbolically, you're going to switch these two rows. And so when you switch the two rows, you can switch them, you can continue using Gauss-Jordan. It turns out that you can achieve a switch of rows by multiplying A on the left by the following matrix. So it's this matrix right here. This guy is known as a permutation matrix. I'm going to denote this particular permutation matrix as P with a subscript of 1, 2. It's not 12, it's 1, 2. The reason why is I'm swapping rows 1 and 2. So right now, I've talked for a long time. It's probably getting pretty tiring. What I'd like people to do is just to check that this is the case. So you have this matrix right here, P12, you have the matrix A. I just like people to verify that P12 times A is A with the rows swapped. So multiply the matrices and kind of see what's going on. Just check it. So right now it's about 10:09. It should probably take 2 or 3 minutes, maybe 5 minutes to multiply the matrices out to kind of see what's going on. So again, multiply on the left by the permutation matrix, P12 times A. What you're hoping to see is that if you take A, the rows are swapped because of the action of the matrix P12. You're multiplying P12 by A on the left. So take a few minutes to do it, about 10:10. Let's meet again about 10:15. Multiply these two matrices. See if you get the right results. I'll turn my camera off now, and we'll get back together in a little bit. Let's so we can get started, I guess. Did people get the right result? Good. So I guess what we're seeing is that when we multiply by P12 times A, all that should occur is that the second and the first row should be interchanged. So this is the first example that actually I don't have the screen shared right now, so let me do that. So the permutation matrix is just a it's just the first, it may be the first example that you see of a matrix that represents a row operation. I use the word represent pretty freely. The idea is that it does the same thing as a row operation. So when you're thinking about swapping rows, what this is saying is that you might as well be thinking about multiplying on the left by a permutation matrix. Notice the permutation matrix is such, notice its shape. The permutation matrix is an identity matrix whose first and second rows have been switched. And so when you're thinking about permutation matrices in general, it's useful to remember that formula. Remember that the identity matrix is a matrix with ones, it's a square matrix with ones along the diagonal and zeros everywhere else. So if you look at P12, notice it's just an identity matrix, but with the first and second rows switched. And the effect of multiplying P12 times A is to switch the first and second rows in A. So it's sort of interesting. So now we've got this matrix. The way that I'm going to kind of gather the terms is I'm going to kind of continue to multiply stuff on the left. If you were doing Gauss-Jordan elimination, at least the pivot that we're dealing with here is not 0, so it's 4. The next thing to do is to eliminate the presence of the 4 in the first row. So to do this, you multiply by a certain diagonal matrix. The diagonal matrix that you multiply looks a bit like this. You can check that if you multiply on the left by this diagonal matrix, if you multiply P12A on the left by this guy right here, the effect will be to multiply the entire first row by 1/4. So that's one thing to verify, I guess. It's probably something we might take a minute or two to do. Probably not that hard to see, I don't know. But it's worthwhile checking the detail, I think. So it's about 1017, take 3 minutes to do it. Take that matrix D, multiply P12A on the left by D. Just notice what happens. So people probably hopefully got the right thing. Can verify that the diagonal matrix D that we're writing down actually does multiply the entire first row by 1/4. But again, you just check it using matrix multiplication. You're going to find out that you get something like this. So notice now we're sort of gathering up factors. We have A. We multiplied initially on the left by a permutation matrix to get a non-zero pivot. If we're trying to carry out Gauss-Jordan elimination, we would then sort of make the non-zero pivot into 1 by multiplying the entire first row by 1/4. That will be achieved by this D1 matrix. First pivot's now 1. If you're continuing with Gauss-Jordan elimination, you probably realize you want to create the reduced row echelon form of A. Below the 1, you already have a 0 in the 2-1 position right here, so there's really nothing to do there. It's the 7 that you would like to eliminate. We're used to an elementary row operation which looks like this to do that. Row 3 is replaced with row 3 plus -1 R1. And so in order to represent that elementary row operation with a matrix, we need another elementary matrix to do that. Neither of the elementary matrices so far do what we want. So what we do is we multiply D1 P12A on the left by a matrix that we'll call E31. So E sub 31, that's not a 31. 31 is a reference to the position that I'm interested in. I'm interested in the position, I'm interested in creating a 0 in the 3-1 position of this matrix D1 P12A. And so it turns out that the elementary matrix which serves to represent this row operation right here looks like this. I'm not sure why I wrote that, so correct that to a 7. Notice that you have a -7 right here in that elementary matrix. That -7 corresponds to the action of multiplying the first row by -7 and adding it onto the third row. So what should occur here is if you take E31 and if you multiply this matrix right here on the left by E31, you're going to produce a 0 in that position, though of course other things will also change. Multiplying this guy right here on the left by E31 emulates, it represents another elementary row operation. So, try this one as well. Again, take a few minutes. work out what left multiplication by E31 does to that product. And in a way, these are the three main elementary matrices that we're going to be dealing with. Permutation matrices, matrices which multiply a row by something, and then in this last matrix, which produces a 0. So notice the character of that elementary matrix, though. E31 has a -7 in the 3-1 position. Don't forget that. So multiply the matrix that we have on the top of the page by E31 and see what you get. Take maybe 3 minutes. All right, so let's take a look at what we've got. So So we were right here, I think. So at this point, remember, we wanted to represent the action of replacing row 3 with a linear combination of row 3 and row 1. And the purpose of that the purpose of that elementary row operation was to use the non-zero pivot that you see right here to produce a 0 where you see 7, and this was the elementary matrix which represented that row operation. Notice that E31 has a -7 in the 3-1 position. When you multiply this entire thing by E31 on the left, what should occur is that you should get something that looks like this. So you wind up getting a big 3×4 matrix, a bunch of fractions, so maybe it doesn't look so nice. But we started with A, and each of these left multiplications, each of these successive left multiplications represents an individual row operation. Now, what's often a little off-putting about this sort of thing is that you're reading these multiplications from right to left. That's got a lot to do with how operations or how function composition works. The thing that is the most left is the last thing that has occurred. So E31, hopefully you got this guy right here. I'd like to basically kind of continue this exercise a little bit further. If you're going and you're using Gauss-Jordan elimination, the next thing to do is to eliminate the 2 that you see right here. And then you would use you wouldn't eliminate it, you create a 1, and then you would use that non-zero pivot to eliminate the positions above and below the 1 if you wanted to create, or if you wanted to reduce A to RREF A. What I'd like people to do, and this may take a little time because it's 3 different things, I'd like people to actually do this exercise. We have 3 different elementary matrices that we've talked about. We've talked about permutation matrices, so we won't really need any of those for the next couple of things. So, which elementary matrices will you need in order to do exactly what is described in this step right here? And in what order do they need to be multiplied? So think for a minute about it. You might want to go a bit further and write down the formulas for the matrices that you intend to use. That shouldn't be too bad because there's not a whole lot of extra multiplication going on, but give that a shot. In order, think about the following. How would you produce a 1 where you see the 2 using an elementary matrix? How would you use that non-zero pivot to produce a 0 above the non-zero pivot in the first row? How would you use that non-zero pivot to produce a 0 below the non-zero pivot in the third row? So there are elementary row operations surely which do this, but the question is, how are they represented with matrices? What matrices represent those row operations? So think about that for a bit. It's about 1031. This might take a bit longer, requires a bit of thought. It's not just a question of multiplication. So right now, 1031, think about it a bit. Let's meet again at 1038. We'll write down the formula. And if you get finished early, yeah.
I think there is a mistake in the matrix that started with E31.
Okay, maybe there is.
Okay, in the third row and the second column, there should have been -3/4, right?
Third row, second column?
The third row, second column.
Right here? Oh, you think it should be negative?
Yes.
Make it negative.
Okay.
In any case, when you're thinking about the next couple of steps, write down the matrices. Which ones, which elementary matrices represent the row operations needed to create a 1 where you see the 2 and create 0s above and below that non-zero pivot of 1 once that's done. Maybe equally importantly, in what order are you supposed to do the multiplication? Like, how do you actually write down the factorization? So try that. We'll meet again at about 1038 once you've decided on that, maybe 1040. then we'll sort of try to finish the problem. If you get done early, if you can do that pretty quickly, see if you can actually completely row reduce this thing using elementary matrices. That's the last exercise. Good. So let's write down the elementary matrices and at least give formulas for these things. You know, and then maybe work on the last exercise, or if people are kind of tired of doing this, then, you know, they can move on to something new. So when you're thinking about this matrix right here, and you are trying to write down elementary matrices, which first of all produce a 1 where you see this non-zero pivot, and then subsequently produce zeros in the 5/4 and the -3/4 position. You know, what should those look like? So to create make a 1 where you see 2, or I guess I should say in the 2 position, we need to multiply row 2 of that big matrix by 1/2. And so I think I'm just going to call the matrix D2. It's another 3 by 3 matrix. And I'm hoping what people realize is that the matrix that will do that looks like this. So before I move on, did most people get that? When you take a diagonal matrix and position that 1/2 in the 2, position, if you were to left multiply the matrix at the top of the, so I'll bring that matrix back up. If you were to left multiply, if you put E1, let's see, I think that right here. If you were to left multiply this matrix by D2, the effect would be to position a 1 where you see that 2 right there for the non-zero pivot. So I'm hoping people got that. When you're thinking about a 5/4 here and the -3/4 here, you're clearly going to have to left multiply by elementary matrices, which are designed to produce linear combinations of rows. So, yeah.
Yeah, I understood that elementary matrix, like I got that one. But then when it was like saying to use the second pivot to eliminate the non-zero entries, I wasn't sure if like all of it was supposed to, be like in one single matrix, like kind of like the other one was, or if like you're supposed to use different matrices.
Two different ones. Two different ones.
And what isn't necessarily, I don't think I understand what it's necessarily asking either.
Okay. So when you're thinking about this exercise, you're trying to write down elementary matrices which represent the row operations which are described in this sentence. So in the sentence, 3 different row operations are described. One row operation involves multiplying the entire second row by 1/2. And I think people will agree that the matrix which represents that particular row operation looks like this guy right here.
Yeah.
So when you kind of combine everything, what we're going to wind up getting, if you multiply this matrix right here, which is the matrix itself that we're writing down is represented by this product. If you multiply on the left by D2, you know, that's how you'd write that down, I guess. So it would be D2, E3, 1, and then the rest, right? D1, P1, 2A. And that would look like, you know, would have the first and the third row would be the same. So maybe I won't write those down, but, you know, it would have a 1, a 5/4, you know, some other stuff. It would have a 0, a 1, and some other stuff, which I don't want to write down, at least right now. It would have a 0, a -3/4, and some other stuff. So I'm hoping that people more or less got that. I'm not really weighing in on what that other stuff actually is because I can't remember it offhand, but does this look okay? So that's the first thing you do. Now, when you're thinking about, you know, the subsequent row operations, which would be needed to eliminate the positions above and below the pivot,
I have the matrix if you want me to say.
yeah, okay. You have the rest of them. You have the rest of the matrix.
I have the rest of the matrix.
Okay.
So three halves, three fourths, three halves, 0, and then -3 halves, and then -21/4.
Okay. So that's the product so far. Now, what we want to be able to do at this point, so we've identified the second pivot right here. We want to be able to get rid of the 5/4 and the -3/4. And so we need to do 2 consecutive row operations to do this. So we need, you know, for the first row operation, if you do things in order, if you try to eliminate the 5/4, you need, what you need to do is you need to take row 1 plus -5/4 row 2, and that's to replace row 1. So let me make sure I've got the sign right. Yeah. So that's the first thing that needs to happen.
So that's essentially utilizing the second pivot. That just means to make it a 0.
Yes. So if you're going through Gauss-Jordan elimination, what you're trying to do is you're trying to look at your non-zero pivots, but you want ones to be those non-zero pivots. So ultimately you have to kind of multiply in some non-zero constant into a row. But then you use those non-zero pivots to produce zeros in the column in which the pivot is located everywhere except for the pivot. So in this example, if the non-zero pivot is 1, the goal is to produce a 0 here and a 0 here. And that's going to take 2 different row operations. To eliminate the 5/4, the row operation that you need, we might have written down yesterday, is something like this. So we take row 1 plus -5/4 row 2, and you replace row 1 with that. The second row operation that we need is to take row 3. So I guess it's plus 3/4 row 2.
Oh, yeah, 3/4.
And replace row 3. Now, what I'm trying to say is that those row operations can be represented by left multiplication by elementary matrices. So the elementary matrix which combines rows in this way will look like this guy. So E31, notice so we were playing the same game, I think, earlier with this matrix. If you have a 1 here in that pivot position and you wanted to eliminate, if you wanted to eliminate that 7, you could multiply this guy right here by E31, but notice the -7 is in this position. The -7 is related to the 7. And so I guess my advice would be to try to play the same game. So if you're trying to eliminate the 5/4, it might make sense to think about an elementary matrix. And I probably should encode it. What position am I really trying to eliminate? I'm trying to produce a 0 in the 1, 2 spot. So maybe we could write that down as E12. And since I am trying to eliminate the 5/4, what I'm going to do is I'm going to write a 1, a 5/4, 0, 0, 1, 0, 0, 0, 1. So, you know, the 1, 2 position, that's where you're trying to create the 0. The 5/4 actually should be 5/4. Yes, -5/4. Should be -5/4 in that position, right? And so what should happen is that if you multiply this matrix by this matrix right here, we should be able to see that a 0 gets produced in that spot. So let's just carry out the multiplication. If you take this matrix, we take the first row right here, times the first column, no real change. If you take the first row times the second column, which is what's going to be left here, you wind up getting a 0. Why is this? Because you have a 5/4. Yeah, something like that. Wait, is that right? Yeah. And then you play the same game here. So I guess you need to eliminate, you know, what's going on below, right? So you want to be able to eliminate the 3/4. So you need something called a, so what is that position? That's 3, 3, 2. You know, you can write down what that is. So does this make sense? Is this more or less what people got? Yes or no?
It makes,
Yes.
I would just have to like calculate the matrix to like see.
Yeah, right. So just multiply it out and kind of see what you get. So is this reasonable?
Yeah, it makes sense.
Yeah. Okay.
So again, like utilizing like elementary matrices, they're just to kind of, I guess, understand the concept rather than,
Yeah. It's surprisingly it's.
because I feel like it's like kind of harder than like just.
Yeah, I agree. And when people see this, they're probably asking, why are we doing this? It's a reasonable question. One reason why we're doing this, and we'll get into this, I think, more tomorrow, you know, when we start talking about matrix decomposition and inverses. When you think about an elementary matrix, so it's on the next slide, and maybe this answers, hopefully this answers the question. So, you know, I'm not going to worry about doing the remaining exercises. Work on those maybe tomorrow, or you can work on them overnight. What I'd like to say is that these elementary matrices all have something called an inverse. You know, we will denote an inverse with this -1 symbol. There are matrices which, these inverses are matrices which undo the action of these matrices. So what do I mean by that? What I mean by that is that if you were to multiply one of these elementary matrices by the inverse matrix to that matrix, then you would get the identity matrix. So the main goal of trying to use elementary matrices is to come up with a factorization for a matrix like A. So you're not trying to do the additional work of row operations, which we understand well enough. The issue is, how do you write down A as a product of elementary factors and that happen to be invertible? So we'll make more sense of those words tomorrow, but that's the point of the exercise. So it's not just to replicate the row operations. It's basically to take a matrix like A and then write it down as a product of elementary matrices. Now, with the sort of work we're doing right here, what we're doing in a sense is we're canceling A with those elementary row operations. Like if you were to continue to do this, if you continued to find elementary matrices and continued to multiply on the left by those matrices, what would happen is that you would wind up with a 3x4 matrix, but the 3x3 part would have ones along the diagonal. You have basically reduced the coefficient part into the identity matrix. And by doing that, you have indirectly found a factorization of A into elementary matrices. So one reason that you want to do this is you want to understand when it is the case that matrices are invertible. You're trying to give formulas for matrices. It's important for theoretical reasons, I guess is what I would say, rather than you know, any practical reason if you're trying to do this by hand. Another reason that it's important is that row operations are computable when you encode them as matrices. So basically, when you're trying to type stuff into a computer, if you really are trying to code up how you row reduce, the easiest way to do this is to multiply on the left by row matrices, because computers understand those things. So there are a couple of reasons to want to do it. What I would say is, if you're trying to do this by hand, it's not obvious why you would do it. But there's a theoretical reason, which has to do with factorizations of the matrix A, which we're going to begin to see tomorrow. And there's also a practical reason. They're inputable into a computer. A computer can understand matrix multiplication, but you know, some of these other instructions that you might give it are a bit less clear. So does this make sense? That's the reason. It's not because the reason isn't because, well, okay, like we want to come up with another weird way of doing row operations. We already have row operations. It has to do with the fact that we want to take a matrix A and we want to be able to decompose it into matrices which are elementary in the same way that you might take a number and you want to decompose it into prime factors. It's the same basic sense that's the sense of the project. It's the same basic motivation. What elementary pieces does A have? And again, the practical reason of being able to input stuff into a computer, that might be another reason as well, but we probably won't be doing that. So does that answer the question?
Yeah, that does. Thank you.
Yeah, so there are a couple of reasons, but what I would say is if you're actually trying to row reduce a matrix, a human being can probably row reduce a matrix much more quickly in your head by just sort of doing the row operations without worrying about the intermediary of elementary matrices. That's not really the reason why you do it. It's because you want to be able to talk a little about what components a matrix actually has. How do you take a matrix and factor it into elementary components? There are good reasons to do this. So are there other questions or concerns about this so far? So is this okay?
Yeah, I think I understand this a little bit.
And so I guess what I would say is that, if you wrote down some more stuff here, you have these two matrices right here. We already have this big matrix right here that we're writing down. D2, E3, et cetera. If you think about what you would append to it, it would be these two matrices from right to left. So it would be E12 followed by E32. So if you take E12, E32 times all of this stuff, what you're going to notice is that in some gross sense, this matrix would look like 1, 0, and some stuff, 0, 1, and some other stuff, 0, 0, and some other stuff right here. What will wind up happening is that this position right here, which is where the third pivot would be non-zero, and you could continue to row reduce with another with a D3 followed by two more elementary matrices. So, you can probably write down exactly what the formulas are. Like if you knew the number, you could actually write down the matrix. So that would basically finish the problem. You would get a product from right to left of a bunch of matrices. So you're left multiplying by a collection of elementary matrices. When you multiply by this big product, when you left multiply A by this big product, you're basically going to get something that's row reduced. So let me write down one or two more things just to sort of finish up. So this guy right here looks like this. If you wanted to go further, and and if you happen to know what was right there, it would probably not be equal to 1. And so if you look at the matrix, so I'll write this as D3. So it's supposed to be E32, E32, E12, D2, E31, D1, P12A. If you're at that point where you have actually created a 1 in this spot, you can eliminate that and that with a couple of more elementary matrices. So I guess you would use E13 to eliminate that and E23 to eliminate that. You have the formulas for this, but this long string of products, you've got this big product out in front times A. This should wind up looking like the following in this example. You should have 1, 0, 0, and some number, 0, 1, 0, another number, 0, 0, 1, and still another number. So the product of the matrices, each matrix encodes a particular elementary row operation that you're carrying out. And so again, there's an idea that there's a matrix which represents something that you're trying to do. And we're going to wind up getting a bit of mileage out of that tomorrow as we finish up the week when we talk about LDU composition in invertible matrices. So those are the main topics tomorrow. There's another sort of ancillary topic, a third set of slides that you can read a little bit about as well. Tomorrow is again pretty technical, but I think I'll probably just sort of focus on 3x3 examples. You can write those down pretty easily. If you want to kind of see where we're going tomorrow with this business about matrix factorization with elementary matrices, it's worth reading both LDU slides. That's slide set, I think 13, 12 or 13, maybe 12. It's the one at the end, right behind WebWork 2 in the week 1 module. And then the one after that, which has to do with inverses. That's kind of where we're going. So that's all I really have to say today. Again, the only important takeaway, the only immediate important takeaway from today is this discussion about elementary matrices. So make sure you have some sense of how those work before tomorrow. There's a question on WebWork about elementary matrices where row operations are represented by those matrices and you have to enter the matrix. They use slightly different notation. On WebWork, they call everything E for elementary matrix. Sometimes, but it's in one of these 3 categories. So you just have to make a judgment based on what you're seeing. You have to use a 3x3 matrix on the WebWork problem to replicate an elementary row operation. That's on the homework that's due tomorrow. So I think that's the main takeaway from today. There's also this discussion of representing linear transformations with matrices, but that's a longer run problem. So I think it's time to stop. It's about noon. So I guess that's all I have to say. So I'll stop recording and